Okay, so let's look at the ideal gas law, and I guess we have to also maybe revisit some of those other gas laws, Boyle's law, so forth, and we'll have to describe exactly what an ideal gas is. So, one, ideal gases are convenient for us. They don't actually exist, but if we make a couple assumptions, and the assumptions are that the actual gases don't attract or repel each other, each individual particle doesn't have a volume. Neither of those things are true, but in normal circumstances, we never get to observe attractions, repulsions, or individual volumes. So our math will always work out to the correct answers unless we have a couple situations. If we have very low temperatures and or very high pressures, gases don't act like ideal gases anymore. They act like real gases, and actually to the point where they may not be gases at all. They may have so much attraction to each other that they may come into the liquid phase, or may even come into the solid phase. So obviously, if you try to use PV equals nRT with a body of water, you're not going to get the right answer. So that's the deviation that we're kind of talking about. Okay. Before we get into some other math, we also have standard temperature and pressure. If you have those situations, you can use the conversion. 1 mole of any gas equals 22.4 liters of any gas. And there is the ideal gas law equation, and it's given to you in your equation sheet. And you just have to kind of keep in mind in the back of your head that if you have those situations involved, when I say low temperatures, I mean low temperatures. So for water, if you have a temperature of minus 10 degrees Celsius, you can't use PV equals nRT, because you don't even, that's going to be a solid, let alone a liquid. It's not going to be able to. You're not going to get any answers with PV equals nRT that are going to make any sense. Okay. So in your equation sheet, it provides you with a gas law constant, 0.08206 liters times atmospheres divided by Kelvin divided by moles. Lots of units, lots of numbers. Lots of textbooks shorten that a little bit to 0.0821, and you'll notice that occasionally I'll do that because that's the way through high school and college that I was provided with the number. But AP, they like to use 0.08206. So if you're taking the AP test, use 0.08206. If you're taking my test with the equation sheets that I provide you, 0.08206. Okay, will it make much of a difference? In the end, it'll probably make very little difference, if any difference, with rounding. But that's the number provided, so I would use that one. Densities. And by the way, I have a few of these answers already done just to make this go just a tiny bit faster, but we'll walk through it. So you do have, this doesn't apply just to gases, but density equals mass divided by volume. This also doesn't apply just to gases. MM is my abbreviation for molar mass from the periodic table. M is mass, and N is moles. So molar mass equals mass divided by moles. And then we also have the ideal gas law. You could combine those as you need to maybe solve for molar mass or maybe solve for density. And these would have to be used in relationship to the ideal gas law. So you need an ideal gas to do this with. So we have carbon dioxide, we have 20 degrees Celsius, we have 1 atmosphere, and it asks for density. So I went on the periodic table and I found 44 grams per mole. Yes, there's a couple decimal places involved, and so it really is 44 point something, but very close to 44. Just so I don't have a ton of room right there. I wrote just 44. 1 atmosphere divided by 0.08206. I put all my units in there, And then if you noticed, I didn't put 20 degrees Celsius. You can't use Celsius in any of these gas law equations. You have to convert it to Kelvin. And to convert it to Kelvin, you just have to add 273 to it. So I did the math there, got all my units to cancel. I had grams per liter left, and I got 1.83. Okay, so it's a little more labor intensive plug and chug, but this is still a plug and chug question. Yeah, so I don't have these all done, but I have a couple of them worked out here. Which of the following gases have the greatest volume? Well, if I look at PVX and RT, anything that's on the left of the equal sign is directly proportional with something on the right side. So I underlined volume in moles because it asks for volume, and one of the three things provided to me is moles. So I thought that was convenient. So moles will be directly related to volume. So whichever one has the most moles is the one that has the greatest volume. So that's already, 0.82 is already done. I don't have to do anything with it, but 24 grams of nitrogen gas, I went on the periodic table, found its molar mass 28, and got a 0.86 moles answer for that. So 0.86 is obviously more than 0.82. And then molecules, you can always use Avogadro's number, 6.02 times 10 to the 23rd, to convert that to moles. And I didn't write my unit in there. So it appears that 0.86 is our highest moles, therefore it's our highest volume. Okay, next question. We have a lake, and we're going to have a bubble rising from the bottom of that lake back to the top. And as it rises, it's going to increase and increase and increase in volume. This is a little more complicated, so to make this go maybe a little bit better for you, I like to circle. You don't have to, but I like to circle all of my either givens or asked of me, and that way I can kind of understand what equation I need to use. So what do we have here? We have a temperature, we have another temperature, we have a pressure, we have another pressure, being asked a volume, and we're given a volume. So now we have to kind of group these together. So it looks like we have a couple temperatures, a couple pressures, a couple volumes. Well, we do know PV equals nRT, right? What would happen if we would divide this by another PV equals nRT? Maybe provide these as circumstance 1 and put maybe circumstance 2 on the bottom. Well, gas law constant is constant, so that's going to cancel out. What else is going to cancel out here? It doesn't say that we're doing anything to the amount of gas. We're not increasing or decreasing the moles of gas, so that's going to decrease. So it looks like we're just going to solve for a volume. You can solve for either volume. I decided to solve for V2, but it would be okay for you to do it the other way. So I'm just rearranging a couple things here to get that. Okay, there we go. So now I just have to figure out which numbers go where. So P1. So rising to the P1 would be like our initial, where we started at. So this is P1, bottom of the lake. Do we have a temperature for that? Oh, we do. Okay. And then do we have a initial volume? Yes, we do. So there's our ones. So obviously these must be our twos. Okay. Now, once we have that done, now it is a plug and chug. I'm gonna move this over here so just give myself a little bit more room. Pressure 6.4 atmospheres. Volume 2.1 milliliters. T2 25 Celsius, going to get you in trouble there. You need 298. So 25 plus 273. Do we have a P2, 1 atmosphere, and a first temperature, 8 degrees plus 273 is 281 Kelvin. So we have to pop all those in there and get an answer. Let's see, 6.4 times 2.1 times 298 divided by 1 divided by 281 equals 14 point, there's a lot of digits here, but it looks like with this math, I could circle more of these, but we have to use the least sig figs, so that's 2 sig figs, so it's going to be 14 milliliters. So our initial was 2.1, our final was 14, and I did say as the bubble rises, it should get bigger, and in this case it did. Okay, don't get intimidated. There's 5 lines of words here. Circle some things. We have a density, we have a temperature, we have a pressure. It says calculate molar mass. So I don't know if you remember, but we had a molar mass earlier, equation for molar mass, density RT divided by pressure. So let's put 7.71 in there. Let's put the gas law constant in there. I don't have enough room for those units. We need a temperature. Oh, 36. Don't get quick with that one. You need to do 36 plus 273. So that's 309. And then what do we got at the bottom? We got 2.88 atmospheres. Okay, so molar mass, that's going to be grams per mole. I take my word for it, all those units will cancel, but if you're not sure, put all those units in there. And it's in the ballpark of 67 point, yeah, we're going to use 68 actually. Okay, so that's the molar mass. And then it says figure out the formula. That sounds like that's going to be difficult. Well, we know it has to have chlorine. We don't know how many. And it has to have oxygen. And we don't know how many. Well, chlorine weighs almost 35.5 grams per mole. So we can't have more than 1 chlorine because that would be that would give us 71, and the whole molar mass is 68. So we know it has to be 1. Now I would not normally put the 1 in there, but we're going to put the 1 in there. So how many oxygens would we need to get us there to 68? Well, oxygen's almost 16. So if we add 16 to that, that doesn't get us to 68. But if we add another 16 to that, I think that's going to get you very, very, very close to 68. Now this is experimental, and you have to get used to this, that when experiments occur, they're not going to be perfect, dead-on answers. But I think this is going to be our best bet for the molecular formula for that compound. Okay, and I think it's a good idea to box your answers so that whoever is grading, me or the AP folks, that they know where to look for your answers. But they also can see all of your work. If you only provide ClO2, molar mass equals 68, you won't get any credit on my tests, and you won't get any credit on the AP test. Okay, so we got Dalton's law of partial pressures. Total pressure equals all the partial pressures. We could keep on going all the way out to infinity with this. D plus E, you know, whatever. We talked about a little bit about gas pressure and how to measure that. One way that lots of people collect gas is, let me show you a little bit here. Here is some water, a big old bucket of water, beaker of water, and then you could have a test tube, you could have a udiometer, you could have any collection device, and this is initially completely filled with water. Okay, the only thing that's going on right now is the atmosphere is pushing down on that water, but there's nowhere for the water to go. It's already up to the very tip top inside that tube. Okay, and then you have some kind of experiment that generates gas, and you have a little tube. Here's our little tube, and that little tube allows gas to come up in there, and it's going to float to the top, and it's going to start filling this up. And as it does, water, let's get our red again, water is going to start coming out of here. That's okay. And you're going to be able to then measure how much gas you have. But the problem is, that's not the only gas. The gas we're worried about is not the only gas that's trapped up in that tube. What's also in that tube is a little bit of water vapor. So we go on a website, we go on a piece of paper table that gives us partial pressures of water at specific temperatures. So if we know the temperature of the water, we know how much water vaporizes at that temperature, and we have to account for it. And we will be solving for pressure of gas. We'll always know the atmospheric pressure. So maybe I go on the website and I find it today at 760 millimeters of mercury. We don't know this one, and maybe we look on the website, and at the temperature that we did this gas collection, the amount of vapor pressure of water, maybe it's 22 millimeters of mercury. So gas pressure, P gas, would be 760 minus 22. So that would be 738 millimeters of mercury. And then we could use that to do any gas law question. Okay. We're not going to get this one too often, but we could deal with this one. Mole fraction. This is the symbol for mole fraction. If you know the mole fraction, how many moles compared to total moles, and you multiply that by the total pressure, you can get the partial pressure. And I think I have one of the questions that we'll get to that does that, so we can see how that works. Okay, so calculate the partial pressures of the gases. I'll do one of these gases. I'll do red, and then you guys can do green, and you can do blue the same way. So we'd have to get the mole fraction first. So mole fraction is part divided by total. There's 1, 2, 3, 4 reds, and then there's a total of 4, 5, 6, 7, 8, 9, 10, 11, 12 gases. So the mole fraction, you could leave it as 4/12 right now, or you could actually divide those two and get the mole fraction of red. But I'm going to just slip it right into the equation that we were thinking about back here. If we want to know the pressure of a gas, mole fraction times the total pressure. So we have the mole fraction, and we have the total pressure, and you just have to multiply those together. So what's that? 0.87 is the mole fraction. Sorry, not mole fraction. The partial pressure for red. Okay, so if you do the blue and you do the green, you can kind of double check yourself in that if you add up those pressures, the 0.87 and whatever you get for the green, whatever you get for the blue, they better equal 2.6, because the total pressure equals all the partial pressures. So we got red, we got green, and we have blue. Okay, Dalton's law question. So again, I'll do one of these. You guys can do the other ones. Calculate the partial pressures of the gases. So I'll do neon, but you do the other ones just the same way. So not partial pressure, mole fraction of neon is 4.46 divided by all the moles. 4.46 plus 0.74 plus 2.15 and what's that come out to be? I think collectively this comes out to be 7.35. So 4.46 divided by 7.35. I'm not going to round at this point. I'm going, well, hardly any rounding. I do have about 6 more digits on my calculator. If you're doing a question, try not to do any rounding until you get to your final answer. So that's the mole fraction. And then here's the total pressure. So here is the partial pressure for neon. Okay. And again, you could do argon and xenon. If you add those three up, it better equal 2. Okay, 5 lines of words. Looks intimidating, but it's not so bad. So what do we got? We have an atmospheric pressure. We have a volume. We have a temperature. It says calculate mass. And what else do we have? We have water vapor. That is the partial pressure of the water vapor. Okay, so remember I was telling you that we're interested in a gas, this case O2, but we have to take into account the water vapor. So let's do that first. So the partial pressure of oxygen is the atmospheric pressure minus the partial pressure of water. So 762 minus 22.4 equals 739.6 millimeters of mercury. Okay, but we're going to want to convert this into atmospheres because our gas law constant is in atmospheres. And there are a number of digits on my calculator, but I just don't have room for them right there. So it's 0.973 atmospheres. Okay, what else do we have? We have a volume, but it's in milliliters. We need liters. Okay, now I think it's a fairly easy question. It's going to start raining here in a second at our house. I'm going to move it into the house here and finish up in here. Okay, so PV equals nRT, and it says solve for mass. So what we're actually going to solve for is moles, and we can convert moles to mass when we get there. So moles equals PV divided by RT. So we have our pressure, and again, we don't want the atmospheric pressure, we don't want the vapor pressure of water, we need the partial pressure of oxygen. So that was that 0.973. The volume, remember, no milliliters, we need liters. That's a decimal place there. Gas law constant 0.08206. Temperature 24 degrees. It tells us it's also 297. There's a lot of places that you can forget to convert here. Okay, so hopefully you can remember to do all those. Okay, so when I do that math, I get 5.1 times 10 to the negative third moles of oxygen gas. So we're going to have to convert that to grams. And to do that, 32 grams of oxygen gas in 1 mole, and then times the answer we just got. And I think that's going to come out to be 0.16 grams of oxygen gas. There we go. So this is a little more labor intensive, and there's definitely a lot of places to forget to convert, but still plug and chug. But now we have a plug and chug with Dalton's law, and we have a plug and chug with ideal gas law. Which flask has the lowest mole fraction? So it looks like it's talking about blue here. Okay, so 1, 2, 3, 4. How many of these gas particles do we have? We have 4 that I already counted. 5, 6, 7, 8, 9. So 4/9. That's 0.44. Blue 1, 2, 3, 4, 5. 6, 7, 8, 9, 10, 11, 12. 5 divided by 12, that's 0.42. And then 1, 2, 3, 4, 5, 6 divided by 7, 8, 9, 10, 11, 12, 13, 14, 15. That gets us to 0.4. So it says which one has the lowest. Well, I think 0.4 is the lowest of our 3 answers there. And then which one has the highest partial pressure of green? Well, partial pressure is going to be directly related to anything over here on the right side, in this case, moles. So if we know how many particles we have, that's going to be directly related to pressure. So let's see what we got here. We have 2 greens out of 9 total. That's 0.22. We had 3 greens out of 12. That's 0.25. And then we had 4 greens out of 15, and that was 0.27. So it looks like for 2 answers in a row, it's this third box here. Okay, and our last question, and this is it's both very easy and difficult at the same time. And the reason it's easy because it uses very simple ideal gas law plug and chug equations, but what makes it difficult is that you have to be able to visualize what's going on, and you have to be able to use these correctly. So let's do that first. Visualize this. So 2 flasks. You can make these flasks whatever way you want. Let's move this up a little bit so I have a little more room to write this out. Okay, so we have a flask, and these are not going to be drawn to scale. There's a flask, and they're connected, and then there's a second flask. It said there's a stopcock. This is just a means to open or close so that the gases can mix or not mix. One flask has 2 liters of hydrogen gas, and it has a pressure of 360 torr. The other flask has 1 liter of nitrogen gas, and it doesn't tell us what that pressure is. Okay, But it says when you open this, let's go and do this. When you open this collectively, when everything mixes, the total pressure is 320 torr. So that doesn't look like that's going to be enough information for us to figure this out. I did give you a hint here. Solve for pH, that's the pressure of hydrogen, using Boyle's law. So what was Boyle's law? P1 V1 equals P2 V2. So what kind of circumstances do we have here? What do we know about hydrogen gas? Well, we know 360 torr. And we also know 2 liters. What else do we know? Do we know the total pressure when this is open and this hydrogen gas can move throughout the entire vessel? No, we don't. But do we know the total volume? We do. It's the 2 liters over here and the 1 liter over here. Again, I was telling you this isn't drawn to scale here. So when you open this up, you get 3 liters. So we could solve for the hydrogen gas when it's open. So it's going to be 360 divided by 3. I think that's what, 120. 120 times 2 is 240. Okay, so the hydrogen gas is 240 when you open up the stopcock. So then it says solve for Dalton's law. So what do we know about Dalton's law? Total pressure. Oh, we have a total pressure. 320 equals the partial pressures. So let's not put an equals there. 320 is our total. We know the hydrogen gas is 240. And then we can then solve for what the pressure of nitrogen gas would be when the stopcock is open. So 320 minus 240, what's that going to be? That's going to be 80. Okay, then lastly, Boyle's law again. So we got the P, we got the V's. Okay, so what do we know now? We know 1 liter, but we don't know that pressure. We'll just call it, here I called it 2 here. I probably don't want to call it 2. We'll go with that. Okay, then over here, do we know the pressure when it's open? Yes, we do. We just solved for that. And then do we know the volume when it's open? Yes, 2 liters plus 1 liter is 3 liters. So I think 80 times 3 is 240, divided by 1 is 240. And there we go. You're definitely going to want to go back and revisit that a couple times. I think this one is both very easy and very, very difficult for what I had mentioned before. It's a plug and chug, but you have 3 plug and chugs you have to do collectively to be able to get this answer right. And that concludes this lesson.